Hello and welcome to this session on digital to analog converters. It's in the ebook chapter 5, so you can have a look through that to try to help you with this. But it's not a bad topic at all, really. It's quite a small topic, and hopefully by the end of this we'll have it pretty much sussed. At the end of this, it leads you on to, well, it asks you to do some questions, and those questions are on a separate document, and it's all in ebook. Okay, so the objectives for this are, by the end of this session, we should be able to analyze and design a digital to analog converter based on an op-amp summing amplifier. Okay, so right. Okay, a little bit of background first. Often we need to change from analog signal to a digital signal or vice versa. I'll just quickly show you this. If I've got an analog signal, music or voice, then it's sort of pretty much all over the place. It goes up and down. It can have any value, and that might represent, that's a bad drawing, isn't it? I'm trying to get my drawings a little bit nicer, but voltage and time here. And this analog signal is a varying voltage which can have any value. If I put that through a speaker, then you'll hear music or voice or whatever. Now a lot of times I need to change that into a digital signal, and the digital signal might look something like this. It might look something like that. So a few ones and then a couple of zeros. 0, 1, 1, 1. So that represents a whole load of digital data being transmitted, ones and zeros. And we have to change between analog and digital to analog quite a lot in our modern world with all our devices that we use, because as we speak, we use analog signals, and our human ear understands analog signals. But machines, computers only store data as binary, digital. So we have to change from an analog signal into a digital. And if I want to play a recording back, which is stored on a computer, then it's stored in a digital format. I'm going to have to change it back to analog so that I can hear it and understand it. When you speak on your phone, you use an analog signal. Your voice is an analog signal. Your phone then changes that into a digital signal so that it can be transmitted across the network. Okay, so that is analog, very roughly analog and digital signals. So now you can pause the video at any point, and I want you to pause it because I really want you to think about the questions that are coming up. So don't just sit there and wait for the answer. Pause the video, have a think about it, do some calculations, whatever, and then play the video again and see if you've got the right answer. Right, so the first part on trying to suss out these digital to analog converters is just looking at some digital signals and analog signals. So we'll start off simple. If 010 represents 480 millivolts, what does 101 represent? So pause the video, have a think about it, and see what answer you can get. Okay, did you get the answer? 1.2 volts. How on earth did I get that? Well, first of all, let's look at this binary number 010. What number decimal does that represent? Well, this column represents ones, that column represents twos, that column represents four. So this number in binary is 2 decimal. So 2 represents 2 is the same as 480 millivolts. So what's this then? Well, that's again, that column represents ones, twos, and fours. So this number 101 in binary is 5 decimal. So the question is, what does that represent? What voltage does it represent? Well, 2 here represented 480 millivolts. So I have to assume that 1 would be 240 millivolts. Because if 2 is 480, then 1 is going to be half that value, it's 240 millivolts. So to answer this next bit, 5, then what does it represent? Well, if 1 represents 240 millivolts, 5 is just going to represent 240 times 5. So that's 1,200 millivolts, or 1.2 volts. So that's how we got that. Okay, so that's a digital signal and a voltage representation of that digital signal. Right, so get a bit of paper and a pen and see if you can draw an inverting amplifier with a gain of -10. We've done inverting amplifiers, and we do need for this topic a bit of previous knowledge. So hopefully you've got that knowledge and you can draw an inverting amplifier with a gain of -10 using an op-amp. So pause the video again, have a go, see what you get. It should look like this. That's what it should look like. So we've got RF, feedback resistor, we've got RN, input resistor, and we've got 10K for RN and 100K for RF, because the gain for this thing, the gain is equal to minus RF over RN. And 100 over 10 will give me 10. And because it's a negative, it will give me a gain of -10. It's an inverting amplifier. Okay, so yeah, we've got to be able to draw inverting and non-inverting amplifiers from memory. That's one of the few things we have to remember. Okay. So yeah, right. Okay, the gain is minus RF over RN. Another way to write it is that the output voltage Vout is equal to whatever's going in times the gain. So I'll just write that slightly differently here. So the output voltage is whatever's going in, Vin, just multiplied by the gain. So, and the gain in this case is minus RF over RN. So this is exactly the same equation. I've just put the minus sign right at the front. You've got RF over RN here, and I've just put the minus sign in front. The reason I've done that is because it fits in better with the equation for the summing amplifier, which we're going to look at in a little while. Okay. Here is a not very good amplifier. So have a think about why this isn't a very good amplifier. Well, if we have a look at the gain here, we said earlier, didn't we, that the gain was minus RF over RN. In this case, it's going to be minus, so the gain is going to be minus RF over RN. So my gain here is minus 120 over 470. So in fact, that doesn't give you a very good gain, does it? 120 divided by 470 is actually equal to 0.255. So this has a gain of, and it's a minus, so it's minus 0.255. So the output comes out smaller than the input, so it's not amplifying at all. That's why it's not a very good amplifier. Okay, so if Vin is 5.4 volts, what's Vout? So pause the video, see if you can work it out. The answer is minus 1.38 volts, because it's 0.255 multiplied by the 5.4, which gives you 1.38. Okay, so not very good amplifier, but we'll see how that works with a digital to analog converter, because with a digital to analog converter we're going to use these inverting amplifiers, but it's not such a big issue if it's not amplifying the signal, because I'm not using it as an amplifier, I'm using it as a converter. So let's see how that works. So here is a summing amplifier. Summing is just adding, so it's an adding amplifier. Basically we've got two inputs now, so it's exactly the same as an inverting amplifier. It's just we've added an extra resistor on there. I'll show you what I mean. An inverting amplifier is just this. With a feedback resistor like this. And all we've done here is we've just added another resistor here. So it's exactly the same as the inverting amplifier. I've just added another resistor. It's drawn slightly differently here, but it's basically inverting amplifier, but another input resistor. Okay, so yeah, that's it. So what we're going to do is we're going to add V1 and V2. So that's why it's called a summing amplifier, because it adds these things. The only problem with this, I suppose, the only thing you've got to watch out for is, yes, it does add them, but because it's inverting, you'll get a negative answer. So if you, for instance, if you had 1 and 2 and you added them, then the result is 3, isn't it? But actually, this amplifier, if it worked that way, this summing amplifier would give you -3, because it inverts the signal. So let's have a look at this. Okay, so we've got an equation here, which is in your equation booklet, so you don't have to remember it. V out is minus RF, so it's minus because it's inverting. RF, the value of the feedback resistor, and then it's V1 over R1 plus V2 over R2. So it's this input voltage here over this resistor here, plus this second voltage here over the second resistor value there. And you add them because it's a summing amplifier. So there's your summing amplifier equation. For an inverting amplifier, V out is whatever goes in multiplied by the gain. So V out is minus V in times RF over Rin. I can change that around, and I can put the RF at the front. All I've done is I've just swapped the position of RF and V in it. So V out is minus RF, V in over R in. You get exactly the same number. It's just, it looks different, but it's exactly the same equation. For a summing amplifier, we've got this, and you can see that actually it looks quite similar. V out is minus RF. Look, we've got the minus RF up here, and we've got the minus RF here. And then we've got V in over R in. Well, that's V in, and that's R in. It just so happens that for a summing amplifier, we've got multiple V-ins and multiple R-ins. So we call them V1 and R1, not V-in and R-in, because that would get confusing. We're going to call them V1, R1, V2, R2, and so on and so forth. But actually, you know, it's really, this equation at the bottom is the summing amplifier. This summing amplifier equation is just the inverting amplifier equation, just extended a little bit. That's the point of this slide. That's what I was trying to show. Okay, so summing amplifiers. Yes, what I want you to do is try and figure out. Pause the video again. Try and figure out if V1 was 6.4 volts and V2 was 7.4. What would V out be? So use the equation. You should get minus 10.1 volts. How does that work? Well, did we say here V out equals minus RF, so it's minus 10. I'll just have to remember that these are, that's cheating slightly. I should really write 10 times 10 to the 3, but I know their K's at the bottom and it will cancel out. It's a little bit cheating, but anyway. V1 is 6.4, so it's 6.4 over R1, which is 10K. If you're not happy with that, put, in fact, do you know what, I'm going to change that, and I'm going to do it sort of long way around. So it's minus 10 times 10 to the 3 multiplied by V1, which is 6.4, over 10k, so that's 10 times 10 to the 3, and then to that we add V2, which is 7.4, and then it's divided by the value of that second resistor, which is 20 times 10 to the 3. Okay, so if you stick that into your calculator, you should get minus 10.1 volts. If you don't, you've plugged it into your calculator wrong. Okay. Oh, that was good. Oh, that's very fancy. Okay, so summing amplifier with digital inputs, 0 or 5 volts. So let's have a look at how this works. Okay, so we have this circuit is based on a summing amplifier, and it will convert a digital number into a voltage which represents that digital number. Now you'll see here that we've got D0, D1, D2 and D3, and those are our data inputs, so they're going to be ones and zeros. I don't know what value voltage they're going to be. Well, actually it tells me at the top it's going to be 0 volts or 5 volts, but it could be 0 and 3 or 0 and 12 or whatever is decided on for the binary 0 and the binary 1. The usual thing is to have binary 0 as 0 volts and binary 1 as 5 volts. Okay, so when we look at these resistors, we have a funny sort of sequence in these resistors. We've got 10k, 20k, 40k, 80k. So you see that each one is double the value of the other one, or looking at it the other way, it's half the value of the other. Now, what that's called is a binary weighting. So these resistors are chosen specifically for those values because each value doubles in size. So just like binary, if I look at a binary number 1 0 1 1, something like that, and this column is ones, this column is twos, this column is fours, and this column is 8s. So each time this value is doubling, and what these resistors are doing is they're in the same sort of sequence. They're halving or they're doubling, whichever way you look at it. Okay, so for this data, which one is the least significant bit and which is the most significant bit? I think that's probably one of the hardest things to sort of do with this, really. And when you look at this, you think, oh, okay, well, 10k is the lowest resistor value, so perhaps that D3 is the least significant bit because that's the lowest value. Well, in fact, it works the opposite way. A high value will make the gain low. So if this value of Rin is high, it makes the gain low. So the higher this value, the smaller effect that this voltage will have. You know, another way to put it is that the bigger the resistance, the smaller the current. So the smaller the current is, the least significance this binary value has. So this is the least significant bit, and this one here is the most significant bit. It's the most significant bit because if I put 5 volts here, it's going to cause more current to flow than if I put 5 volts here. 5 volts here will cause less current to flow up there because it's a bigger resistor. So that's the least significant bit, and that's the most significant bit. So the resistors are binary weighted. Okay, that's exactly the same as last time. Okay, so if D3 to D0 is 1 0 0 0, what is V out? Okay, so have a think about that. Pause the video. V out is minus 5 volts. I'll show you why. D3 to D0 is 1 0. So D3 is a logic 1 these are all logic zeros, and a logic 1, it says up here that a logic 1 would be 5 volts. So these are 0 volts, 0 volts, 0 volts, logic 0, and a logic 1 will give me 5 volts. So really, I suppose really this lot here is not really doing anything because there's 0 volts going into it. So that lot doesn't do anything. So actually what I've got is I've just got an inverting amplifier with Rin 10k and RF 10k. So that gives me a gain of -1. The gain for this, if all these are zeros, then they're not having any effect on anything. So this is just an inverting amplifier with a gain of -1. If I put 5 volts in, then I get -5 volts out. Because 5 times -1 is -5. Okay. What? Slightly different then. Okay, so D3 to D0 is 0, 0, 0, 1. So what's V out now? So see if you can work it out. Pause the video. And if you got -0.65, then you are absolutely fantastic. So what am I going to have here? Basically, D3 is a 0 volts, 0 volts, 0 volts, and 5 volts, because D0 here is a 1. That's how we're doing it here. D3 to D0, so that's going to be D3, D2, D1, D0, like that. So D0 is 5 volts. What have I got? Well, if all those are zeros, then they're not going to come into it. All this lot doesn't come into it really. All those other three, and what I've got is I've got a gain of minus RF over R into it. So I've got a gain of -10 over 80. So a gain of an eighth minus 0.125, and if that's 5 volts, then 5 multiplied by -0.125 is my -0.65 there. Okay. Okay, so we've got a different scenario here. We've got all of these as logic 1. So all of these are 5 volts. So we've got 5 volts here, 5 volts on each one of these because they're all logic 1s. So logic 1s in this case is represented by 5 volts because it tells me up there. In some questions it will say, oh, logic 1 is at 10 volts or something, so you just have to change these to 10 volts. So so how do I work out what V out is? Well, again, pause the video and see if you can use the equation to try and work out what V out is. And I'm going to do it here. So using the equation, V out equals minus RF, and then it's V1 over R1. So it's 5 over, I'm sort of mixing this up a little bit. I'll do the equation first. So so it's V1 over R1 plus V2 over R2 plus V3 over R3 plus V4 over R4. Long equation, but it's fairly simple. So V out is going to be equal to minus 10, because RF is a 10k. So I'm going to cheat here, but I know it's 10k, but the 10k's at the bottom are going to cancel out, so I can put them all as just the numbers. I'll show you what I mean. So V1 is 5 over R1 is 80, and because it's k here and k at the bottom, I can just leave them out. It's cheating a little bit, but if you want to, you can put 10 times 10 to the 3 and 80 times 10 to the 3. You'll get exactly the same answer. 5 over 40 plus 5 over 20 plus 5 volts over, and the last one is 10k. And if you put that all into your calculator, then you will get You ready? Minus 9.375 volts. Now I'm going to show you a different way of doing this, and this goes back to what we were doing right at the beginning. So right at the beginning, I was saying, I gave you a sort of scenario of, oh, well, you've got this number, this binary number represents this voltage. What does another binary number represent? Right at the beginning, we did that, and we're going to do the same thing here. So what I'm going to work out is what would, if it was just the least significant bit and all the rest were zeros, what does the binary number 0001, because don't forget this is the least significant bit, it's got the biggest resistor, that's the most significant bit, it's got the smallest resistor. What voltage out would that give me? Well, it would give me 5 multiplied by the gain of this thing, and really, again, this lot aren't doing anything, are they? They're not having any contribution at all to the output V out, because they're all 0 volts. So it's 5 times the gain, which is, and the gain would be minus 10 over 8. So that would give me, what would it give me? It would give me 10 over, sorry, it's 10k over RF over 80. So it's 0.625. So it's minus 0.625. So if I just had 0001, then I would get minus 0.625 volts at my output. So what would happen if they're all ones? Well, what does this number represent? Well, that's a 1, 2, 4, and an 8. So this number is the number 15. So if 0001 gives me 0.60, sorry, that's not very clear, but it's 0.625 volts. If that gives me 0.625 volts, then what does 1111 give me? Well, it should be pretty easy to work out, because 1 gives me that, so 15 would give me 15 times whatever just 1 gives me. So it's 15 times minus 0.625. And that is going to be, I'll do it on my calculator, 15 times 0.625, and that gives me 9.375, well, it's a minus, keep forgetting the minus 9.375 volts, which of course is what we got from when we used the big long equation. Okay, so there are 2 different ways of doing it. If you want to work out any value, what you can do is just multiply by the value that you get when it's only the least significant bit, and just multiply it by whatever number's going in. Okay, so this last bit here, this 0.65 is quite important, really. The smallest step that this can have is minus, what is it, minus 1.25 volts. Get rid of all of this. Okay, so just going back to this for a second. So 0001 gives me an output of, I've forgotten, an output of divided by 8 times 5. I want to get this right. Minus 0.625 volts, and this number is quite important. So it's what the least significant bit, if only the least significant bit was high, that would be the output, and that's also called the resolution. So that's an important part of analog to digital converters and digital to analog. This is a digital to analog. The resolution is important. So this can resolve down to 0.625 volts. The smallest step size is 0.625 volts. If you change Yes. Okay. That's it. That's the resolution. Okay. Okay. So now, now we've got all of that. We don't have to use the summing formula. You can do if you want to. Once you know the smallest step size, you can just work out the output by multiplying the step size by the binary number. So again, pause the video, see if you can get these right. We're going to use 5 volts and 0 volts again, and D3 I think we said was the most significant bit. So that's the most significant bit there. Well, the binary number is written normally, that's the least significant bit. So and that number is, what is it? It's a 1, 2, and an 8. That number is 11, and this number is 5. So what's V out if I put 11 in? Minus 6.875. And what is it if I put in a 5? It's minus 3.125. Okay, so if you didn't get that, go back and see if you can work it out. Okay, so so that's it in terms of digital to analog converters. It's not too bad. Hopefully I didn't make too bad of a mess of that trying to explain it. But have a look through the video again if you like. And the exam questions, there are just 3 questions on a document on eBrock. So have a go at them. And what I'll do is I'll post up the answers to those questions in a couple of days. Okay, see you next time.